Okay, so next speaker is Christian Schmeiser, and he's going to give us a talk about Decay equilibrium with diffusive and kinetic transport.
Thanks for the introduction, and thanks to the organizers for the invitation. Actually, the first small part of my talk fits very well to what Giuseppe just said. So I will talk about long-time behavior of various linear equations, actually, and the goal is to talk about linear kinetic equations. However, the approach involves some knowledge about their macroscopic limits in a way, and these macroscopic limits are typically Fokker-Planck equations. And as Giuseppe said already, the status of the theory for the long-term behavior of Fokker-Planck equations is not so satisfactory, not so complete. So you will see that actually for what we wanted to do here, some of the things we had to do ourselves, and as you mentioned, this work of Feller, this we weren't aware of. But however, what we talk about situations with constant diffusivity, so we this is not a question, but you will see that there are other issues which are.
Feller was not considering last time behavior,
but from fundamental solutions,
we are safe.
You can get it. So this whole enterprise started with the work between Jean Dolbeau, Clément Moreau, and myself on hypocoercivity for kinetic equations, and you see the group has been increasing since then. It still is, and I will mention various works with various subgroups of these people. So let me start with the Fokker-Planck story. So, if you saw Fokker-Planck equations different to Giuseppe, I will always have the diffusivity just one. So that is I only play with the convection field, and the convection field will always be the gradient of a potential. And I start with a very, as it has been mentioned several times, it's a school. So I start with the best known situation where you have a confining potential which grows at least linearly. This notation I will use several times. It's 1 plus x squared square root is this bracket, and so this bracket x to the gamma grows like absolute value x to the gamma at infinity. So we have, if we have at least linear growth, then things are well known. You have an equilibrium distribution, and you have exponential convergence to this equilibrium distribution. The classical big story about this is the gamma calculus developed by Bakker and Emery. But essentially, the only thing you need is the Poincare inequality, and for the Poincare inequality, actually, this gamma greater equal 1 is a sharp condition for its that it's satisfied. So you cannot afford a sublinear growth of the potential for that, and that brings me already to the limitations. So I want to look at various other cases. First of all, completely at the other end, no confining potential at all. So what is the asymptotic behavior then? You just have the heat equation, everybody knows what the asymptotic behavior is. So I'm always interested in L2 based results. So I write what happens in the L2 term. So you have complete dispersion, everything goes to zero algebraically with this rate. There's basically two options to prove that. One is straight is more or less explicit solution by a Fourier transformation, and look at the Fourier transform. For many aspects, in a way more elegant, is using the Nash inequality. Actually, Nash developed the Nash inequality exactly for this reason, so he tried to understand this problem. I've written the Nash inequality here. You see, it's a bit like Poincare. It relates the L2 norm of the gradient to the L2 norm of U. This, in our situation, is just a constant because we have a mass conservation of the Fokker-Planck equation. So it does the same job, except that there is no real linear relation between the two there. It comes with an exponent a here, which is the dimension of the dimension over 2. So the result is not quite good as the Poincare inequality, and that is the reason why you only get algebraic decay here. Okay? So that are the simple cases. But now the question is, what about cases in between these? And that was the surprising thing for us, that there is not so much on these cases in between. So one case is when you have a sublinear growth of the exponential, you still have an equilibrium which is kind of sub-exponential. So you have an e to the minus v is the equilibrium, so it does not decay exponentially. It's already pretty complicated to get some good results of the decay to equilibrium, what kind of decay you get. What you need is typically extra assumptions on the initial conditions, and there is various ways of doing it, and one work a while ago has been by Liggett using weak Poincare inequality, where you basically interpolate here, it's a bit like in the Nash, but you use the L infinity norm here for interpolation, so you need some extra L infinity estimates. Another option is to use so-called weighted Poincare inequalities, where you have, instead of such a factor, you have an extra x power here. And for this weighted, what you need then is extra assumptions on the initial data, which are like moments, but it's not moments, it's a weighted L2 norms you need bounded. So for the initial data, and you have, if you have enough of these extra norms of the initial data bounded, you can get actually arbitrarily strong algebraic decay. It depends on how many of these extra norms you have bounded. So this is why I wrote t to the minus infinity here. Of course, for a certain initial data with certain assumptions, you get some exponent here, but in principle that can be arbitrarily large. So Cavion and Michel have worked on that, and we have kind of simplified this. If you see the rows like that, this corresponds to the people I mentioned in the beginning. So in this case, it's Moin, Dolbeau, Laflèche, who is a student of Stéphane Michler, Clément Mo, and myself. So that would be this case. And then another case which we have looked at is where you have a very weak confinement. You just have a logarithm here. And actually it is so weak that this is gamma less than d, that the equilibrium e to the minus v is not even in L1 anymore. So that means that is a situation like for the heat equation where you expect the dispersion of the solution, right? The solution will go to 0. But again, the question is, what's the decay rate, and a result we got together with Émeric Point and Jean Dolbeau is such an algebraic decay where this gamma features here, and that is exactly what you expect. For gamma equals 0, you have the decay like for the heat equation, that is when you're, there is no potential, and when gamma tends to d, the e to the minus v is closer and closer to something in L1, so you do not expect decay for gamma equal d. Or at least maybe for gamma equal d, maybe yes, but definitely not for gamma bigger than d. So that is a result here. And I don't write all the inequalities which we use. I only gave you the very basic ones. The ones which is used here is a weighted Nash inequality, which can be also interpreted or seen as a special case of Caffarelli-Kohn-Nürnberg inequalities. So we use lots of different inequalities here, and most of them are special cases of Caffarelli-Kohn-Nürnberg. So Caffarelli-Kohn-Nürnberg is interpolation inequalities. Basically what we mostly use is this weighted Nash, which are inequalities like this, but where you have powers of x weights in each integral weights, and there's a big numerology and what these powers can be and so on. I don't want to bore you with these details, which I'm always usually ask John Dolbeau and some of that. He's my inequality guru. Okay. So that was the story about the Fokker-Planck story. But now what we really want to do is look at kinetic transport equations. And actually very simple, just linear. A collision operator here on the right hand side and an accelerating field on the other side. So in principle, this capital V here plays the same role from a physical point of view as before. For the collision operator, we allow various choices. Linear, as I said, could be relaxation operators, or it could also be a Fokker-Planck operator, but now the collision operator acts on the velocity variable v, so that would be a Fokker-Planck operator in the v direction. Properties we always ask is mass conservation, and actually we ask that mass is the only conserved quantity here. So, which on the other hand can be expressed in the fact that we expect that there is a probability density with the zero mean, which spans the null space of the collision operator. And we also assume that L is the propagator of a Markov process, and by a very general result of Markov processes that says that relative entropies are non-increasing. And the simplest relative entropy is the weighted L2 norm here. So if L is a propagator of a Markov process, that's a consequence actually. Okay. So which is the semi-definiteness of the operator. Okay. Yeah, and just for notation, we look at the orthogonal projection to the null space, orthogonal with respect to the scalar product in here, and that I call P. That's the right hand side, and the other part of the equation is the transport operator here. And an observation is if I use this same norm here and weight e to the v in the x direction, then this transport operator is q-symmetric. Okay. So what can we do for a long-time behavior of equations like this? And what I want to tell you shortly is something which has been done a while ago, much longer than this number indicates. The paper has been in the pipeline for first submitting, then refereeing, and so on for a number of years. So the whole story is quite a bit older. It is an abstract approach for proving decay to equilibrium for equations of the form which I have presented before. However, we go to an abstract situation where we just have an ODE in Hilbert space, and we write the equation in the form which we had before, with one operator on the right hand side, one operator on the left hand side. I will refer to them as collision and transport operators as before, but now it is an abstract story. And we will just make several assumptions on these operators, and from that infer convergence to equilibrium. So like before, as I mentioned, we assume the T operator to be skew-symmetric. Now we are in an abstract Hilbert space, so antisymmetric operator here, and a negative semi-diff operator on the right-hand side, which if you put the projection to the left or right, both cases, you get 0, where this here is an extra assumption in a way. Well, we could also assume just symmetry of this operator, then that would be the same. And we allow both of these operators to be unbounded possibly. From what we said here, we have what in kinetic theory would be called the H theorem, is that the norm is not increasing, which in this case has the norm squared, is like an entropy here. Is not increasing. However, by the semi-definiteness of L, you see the T doesn't enter, only the L enters, and it's already clear that from what we said that we cannot have any coercivity, so we cannot deduce convergence just from this. Okay? And convergence to equilibrium has to come somehow from the action of the transport operator also. So the question is, how can we get some results strengthening this in a way? And a term which has mostly been made popular by Cedric Villani in this context is hypocoercivity. So that basically says roughly, if you have a situation like that where you have no coercivity, but you still have exponential decay to equilibrium, then the problem would be termed hypocoercive. And now the story is to devise a method to prove hypocoercivity in this case, and the idea is just to modify the entropy a little bit. So we take the entropy, which we had before, and we add a little correction. And the art of the story is in producing this auxiliary operator A here, and I wrote it here. Looks a little miraculous, right? But it only contains symbols which you saw already. It's the projection to the null space, the transport operator, and here what this is just a bounded operator you put on top. Remember, I said that the transport operator is allowed to be an unbounded operator, which it is in the kinetic situation where it's a differential operator. However, we want this to be something which is equivalent to the norm in principle, so we want the A to be a bounded operator. And that is one of the main reasons why we put this factor in front to make this whole thing bounded. And now the main part of this A operator is this TP star here. And that comes, you see why when you compute the time derivative of this modified entropy, you get one term which is this, which we know already, that comes from the original entropy, and the second important term is this one. And when you look at what this ATP is, you look at the A here and you add a TP here, and then you see basically what you have in the function Z over 1 plus Z. But applied to this operator TP star TP. Okay? So that is the TP star TP is clearly a positive semi-definite operator. So that is another good term here. It's a negative term on the right hand side. The idea is that these two terms together now produce the coercivity. Unfortunately, this comes at the cost. We get several other terms in the time derivative, and one part of the game is to control these other terms. Okay? Now, the whole story relies on a certain algebraic assumption, which is this one here. That if I apply the transport operator to the projection, and then again the projection, that I get 0, the question is, what is the interpretation of this assumption? And if you do the computation for the kinetic model, then you see this assumption exactly means that the mean velocity of the equilibrium distribution in velocity is 0. So, in other words, if you do macroscopic limits for the kinetic model, then you get a diffusive behavior. So, in this algebraic setting, this assumption PTP equals 0 is exactly translates to that the macroscopic limit would be a diffusive limit. If you would do on the abstract equation which I have, let me go back here. If I would put an epsilon here and then try to find a good power of epsilon in front here, with this extra assumption PTP equals 0, the good power would be an epsilon squared here. So that corresponding to a diffusive field scale. Anyway, having that, with this extra assumption, we already have two important results. First is we knew already more or less that the A is bounded, but we get an explicit bound, which says that if we choose delta small enough, then this is really equivalent to the norm F squared. And then one of our auxiliary operators here, the TA, is also bounded, which we get in any case. The work which remains to do is to see how much good this does to us, and to control the remaining two terms here. And all these we put in the abstract setting, we have to make as assumptions. So the first assumption is what we call microscopic coercivity, so that this L is not only semi-definite, but is really coercive with respect to the microscopic part of the distribution function. Macroscopic coercivity is that this operator TP is coercive with respect to the macroscopic part of the distribution function. So it is very, very easily understood, right? In the evolution, you could have that F goes to PF, becomes PF at some point. So it is in the equilibrium of L. And then, but that is not the final equilibrium typically. So you need that now the transport has to act, has to do something. And this just says nothing, then the transport does something if it acts on PF. Right? So the evolution, if PF is not yet 0, that you are not, yeah, by the way, here I have normalized everything that the equilibrium is 0, sorry, I forgot to say that. So if the PF is not yet 0, then the evolution doesn't stop. This is the main message of this inequality here. And with what I said before, this immediately gives you a what we need for the good term here, that some extra coercivity. Then I said already the diffusive macroscopic limit, and then I had these 2 extra operators, and what we need is boundedness of these 2 extra operators, which is sometimes a bit of a surprise that this is typically true. So we'll have to show that even if L is a Fokker-Planck operator, that this is true, which is a bit of a surprise that it works, but it works. I will not go into the details here. Anyway, so now what is the result? Under all the assumptions which here we have on the last page, the norm decays exponentially, and actually the exponent, the constant in the exponent can be computed. There can be given numbers explicitly in terms of just the quantities we had which we had in our assumptions before. One application of this, which we already had in this paper together with Dejean and Clément, was the standard situation, which corresponds to the standard Fokker-Planck situation which we had before. So we take a nice collision operator with a Maxwellian equilibrium, and we take the confining potential at least linear, then we get exponential convergence to equilibrium from this theory. But now the actual story I want to tell you about is what if if some of the assumptions are not so nice, some of the contributions are weaker. And the first, and I will walk you through this simple example, and then at the end give you some other more recent, some more recent result. So this simple example is just a very simple relaxation operator here and no confining potential. The macroscopic limit of this equation is just the heat equation, so you expect decay like the heat equation for the long time behavior. I have to be a bit faster here, but it is rather easy to understand, I think, in principle what we do. We do the same as before, okay? The interesting thing is now we do not have the macroscopic coercivity, right? The macroscopic coercivity before was like corresponded to the Poincaré inequality, which we do not have now. So, but what we still can do is we can estimate our remainder terms which we had by the 2 good terms here. So these are essentially the 2 good terms which we have. And all we need now is, instead of the Poincaré inequality, the Nash inequality, to get an estimate like this. But now this phi is a nonlinear function. It's not, so we do not have a linear dependence. And that gives, essentially, it's exactly of the kind which we get from the Nash inequality. So we get the same decay as for the heat equation for this kinetic model. And let me maybe skip that. Or just say it in words without, you don't need to read the formulas. If you put some extra assumptions on the initial data for the heat equation, right, say that the mean is 0 or some moments are 0, then actually the decay rate increases, and the same kind of result you can do here. You need that if you integrate the initial data against the polynomial, you get 0, then you get a better decay rate depending on the vector of the polynomial. And on my last slide, I have a few extensions of the story. Remember, I talked to you about this case for Fokker-Planck. So we can raise this whole thing also to the kinetic level, and again get the same kind of decay on the kinetic level. That was a work with Bois and Dolbeau. Then what the next story is, put for the collision operator, the Fokker-Planck operator with a sub-exponential equilibrium. Okay. Now without confining potential, then you get an algebraic decay result, where the best you can get is, I mean, this is in velocity direction, right? So you are still limited by the heat equation behavior. So the best you can get is decay like the heat equation, but typically it will be worse. And finally, still work in progress is having a velocity equilibrium which does not have a second order moment. So algebraically decaying not a second order moment. The experts know that the diffusivity in a diffusion limit would be just the second order moment of f. So that is an equation which does not have a diffusion equation as a macroscopic limit. The macroscopic limit would be a fractional diffusion equation. And here the modification, there we need a modification of this hypocoercivity approach, which is not so trivial, and of course I don't have time to talk about it. Thank you for your attention.
Questions? Comments?
In the next case, in the case of the fractional diffusion, so you start from the Boltzmann equation, linear Boltzmann equation with this Decay distribution, right?
Mm-hmm.
And you get an explicit rate of convergence to the fractional diffusion in X.
For the fraction, for the fractional diffusion equation, it is known what the decay is, and that is what you expect. So that is the goal, right? But to show proof that.
And you have an explicit rate.
Here, yes, we can get some explicit rates, and I'm not completely sure if we get precisely to what you expect from the fractional diffusion, but that's the goal, as I said. Yeah. So this is, there are several issues which are not completely clear yet.
So in the assumptions you had pi t pi 0 for the diffusion case.
Yes.
And for the fractional diffusion, what's the subtract assumption?
Sorry, say that
This
again.
PTP.
Okay, that is exactly which needs to be modified.
Yes.
Right? Because this you cannot even compute because it requires a second order moment. So that is where this A operator which I had, this needs to be modified to kind of get the fractional diffusion behavior in a way.
So in this work you have done this abstract setting as well for the.
No, it is there. What we do is we work on the Fourier transformed equation and do a mode-by-mode analysis on the Fourier transformed equation. Forgot to mention that. Many of these things, what I did with the Nash inequality for the kinetic setting, you can also do, like for the heat equation, you can also do with Fourier transform. And in this fractional diffusion situation, we work with the Fourier transform. But yeah, it would take too long to go into it.
What about the domain of attraction? Which amount of initial data can you use?
I don't have a precise answer ready, but you will need some kind of decay properties also. So for the
This is the usual situation.
Yes, yeah. Okay. Yes.
The main difficulty is V depends on time. So the potential depends in time. If we calculate.
If the potential depends on time. Cool. If the I don't know. And I mean, then what is a steady state, right? You would have to assume that the potential also has some convergence as t tends to infinity. Otherwise, right, in order to be able to talk about it. But it produces, well, it is maybe not so bad if you have an explicitly given potential. Right? The interesting case is if you couple with some, if you have a mean field model where the potential say, and actually there is some work now by several people here also that on the Blasov-Poisson situation where you couple with the Poisson equation. But if you have a given explicit potential which converges as t to infinity in a good enough way, then basically it just produces a small inhomogeneity in your equation that is not so bad in your estimates.
Okay, so let's thank Christian again.